maybe let me start. Yeah. Okay, let's start. Today we have a lot to cover. And so maybe I speed up a little bit. So in the last lecture, we talked about this symmetry and the dual symmetry. Basically, it's order operator and the disorder operator. And so in particular, for a system with a symmetry, ordinary symmetry, it always have a dual symmetry. And the issue is how to see the both symmetry explicitly. We mentioned that one way to see them explicitly is to view our symmetric system as a boundary for one higher dimensional system. The one higher dimensional system is in a trivial symmetric product state. So it's symmetric, but it's product state. So basically, you can remove them. But then after we include them at one higher dimension, we can gauge the symmetry in one higher dimension and get a G-gauge theory. In the G-gauge theory, the symmetry, dual symmetry will be explicit because the gauge charge is the original symmetry charge. The gauge flux became dual symmetry charge. So this is a way, gauging in one higher dimension is a way to see both symmetry, dual symmetry explicitly. And so this became very useful, very important. So we want to using that picture to look at the symmetry. And so it's a more general way and a more complete way to understand the symmetry. So this we are going to use this picture. And so in general, this works. And for any symmetry in any dimension, we can just view this symmetric system as a boundary of a symmetric product state in one higher dimension. The bulk has a very high energy gap. Then we gauge the bulk. And then the boundary may have low energy. The bulk have high energy. So low energy effectively only involving boundary. And this boundary theory will be this symmetric theory we interested in. And this bulk gauge theory or bulk topological order or bulk TQFT is called so-called categorical symmetry. And this picture works even for anomalous symmetry, because for anomalous symmetry, and we can view as a boundary of SPT states, which we did not really discuss in detail, just mentioned this. We know the anomalous symmetry cannot be gauged. But however, when you view anomalous symmetry as a boundary of SPT state with the symmetry, and this symmetry in one higher dimension is an on-site symmetry, can be gauged. So therefore, we can do the same thing, we gauge the symmetry in one higher dimension. And because of SPT order, the higher dimension theory is a diagram Witten theory with a co-cycle twist. So there's co-cycle twist. So therefore, even anomalous symmetry can be understood this way. And also this kind of holographic picture, maybe one thing is that this holographic picture works for discrete finite symmetry. For continuous symmetry, we have trouble because gauge theory in one higher dimension for continuous group is gapless, and then we don't have an energy scale separation. And so this holographic picture have some problem for continuous symmetry. But for finite symmetry, this holographic picture immediately predict or imply so-called beyond group symmetry, some symmetry which is not described by group. They're very simple. That's when you have a non-abelian symmetry, the dual symmetry, we have a point charge, but the flux in higher dimension can be string or membrane. So in 3 dimension, the gauge flux is a string. In 4-dimensional space, the gauge flux is a membrane. So it's a higher dimensional object. So therefore, this higher dimensional object really gave rise to this higher symmetry at the dual symmetry of original zero symmetry group. The G describes the zero symmetry, and we have D-1 higher symmetry in D-dimensional space. But the point is that this D-1 symmetry is actually higher symmetry only for abelian group. For non-abelian group, you know that for non-abelian group, the charged particle have a fusion according to the representation. And then the string objects, gauge flux would fuse according to the conjugate case class, because gauge flux have degeneracy, the gauge flux described by group element. But the different group element in the same conjugate class are degenerate, belong to like a different component of same thing. And the fusion of conjugate class is non-trivial. And so that means this higher symmetry actually is not abelian, because for higher group, the higher symmetry always abelian. It's a requirement for some reason. But this gauge flux in for string and the membrane, their fusion is not abelian. And so it's something beyond the group. So it's very natural. The dual symmetry of a non-abelian symmetry actually is already beyond the group symmetry, beyond the group higher symmetry. So that's kind of macroscopic picture from this holograph picture. We can actually, it's easy to construct a microscopic theory on the lattice, which realizes a higher non-group like symmetry. It's very simple. We have some random lattice, but the degree freedom live on the link. We call it Gij. And then we pick a representation. This Gij is an element of a group, some non-abelian group. Okay. Then we just pick a representation of this group. This RQ is representation labeled by Q. Then we construct a Wilson line operator. So this is basically Wilson line operator. We view Gij as a gauge connection and link. This becomes Wilson line operator, you know. And that's it. We view this Wilson loop operator as a symmetry generator. Then the local symmetric operator are those which commute with those Wilson loop operator for arbitrary loops and for arbitrary representation. That select a so-called locally allowed operator. This is called local symmetric operator. Then the Hamiltonian will be a sum of a certain subset of local symmetric operator. Yeah. So and then you can show that the product of two transformation is do not give us the third transformation and give us some kind of fusion rule of representation. This Nijk is now NQ1, Q2, Q3. It's some kind of fusion coefficient, and which is really given by the fusion coefficient of a representation RQ. And so this non-trivial fusion coefficient really say that the composition of a two symmetry transformation do not satisfy group law. So it's kind of fusion ring. And only when the symmetry group is a abelian, then this Nijk is only one term here. For non-abelian, there's several terms in the sum. And that's it. So that is a very simple way to have an example of a non-group like beyond group like a symmetry. Yes.
So what would be the charged object in this construction? So this is a symmetry generator.
Yeah, the charged object is actually so this is also, I think it's a flux, it's a gauge flux. Yeah. Mm-hmm. Yeah. So I did not write it down, but it's generated by the gauge transformation. Uh-huh. So you can do the gauge transformation on certain region, local region. Uh-huh. Then the boundary of this gauge transformation, local gauge transformation, is will be this loop of charge object. Uh-huh. for this kind of things. Yeah.
So here G is taken to satisfy the co-cycle condition, right?
No, G is there's no co-cycle here. The G just a group.
Yeah, so Gij is assigned to satisfy the co-cycle condition here.
Gij.
No.
Maybe eventually, but here there's no gauge theory. Uh-huh. Here I'm thinking this is like a lattice model. Gij just a group element living on the link. There's no other condition. Then all the condition one mentioned is when you have a Hamiltonian, the Hamiltonian determines linear dynamics. Mm-hmm. Whether the ground state satisfies condition or not depend on Hamiltonian.
I see.
Here I did not even write down the Hamiltonian. I just write down the symmetry. Then whatever Hamiltonian formed by this local symmetric operator will be the symmetric Hamiltonian, but the symmetry may or may not be spontaneously broken. So depend on Hamiltonian. Yeah.
Sorry. So if I take for example just the usual non-abelian Yang-Mills theory on the lattice,
yeah,
what phase is that in?
I think that phase is this loop condensation, loop condense. So basically, that's a spontaneous symmetry breaking of this kind of higher symmetry, because of this, and that's related to this flat connection. Because when you have connection, the Wilson loop operator all become one. So but however, when you wrap around the system differently, they do not commute. So that's a spontaneous breaking of this algebraic higher symmetry. Yeah, very good question. Yeah. So therefore we have this symmetry which is beyond the group. Remember that when we have a group-like symmetry or even higher group-like symmetry, we know how to compute is so-called categorical symmetry. We know how to compute topological order in one higher dimension, give this holographic view of symmetry. But for the beyond the group symmetry, we have trouble because we don't know how to gauge. Yeah. But there's a more fundamental, more basic way to compute this categorical symmetry. So it's really that. So what is symmetry? Symmetry actually is algebra of a local symmetric operator. So-called symmetry is a way to select so-called a set of local symmetric operator. So whenever you give a set of local symmetric operator, you have a symmetry, you know. So somehow but you may say, maybe I don't have symmetry. So what kind of symmetry, if you have or have no symmetry, depend on is a property of this the set you choose. So it's a property of the algebra of a local symmetric operator. Yeah. So from here, actually, you can extract the symmetry. So I denote both the symmetry and algebra using R, because these two are really almost the same. Then what is the idea? Idea is that although this is an algebra local symmetric operator, this algebra contains extended operator. Because in higher dimension, in 0 dimension, that's it. You have local operator, product local operator is local operator. But there's spatial dimension, which is very important. Then you ask yourself, what's new in higher dimension? Because in higher dimension, you can have local operator and local operator, local operator, local operator. You can multiply many local operators and get something very extended operator. So this is a new feature in higher dimension, and one should emphasize this feature. And so actually, in higher dimension, the algebra of a local symmetric operator contains extended operator. And then from this extended operator, they have a special thing. We can derive so-called braid fusion category. Actually, it's non-degenerate braid fusion category. And this non-degenerate braid fusion category corresponds to topological in one higher dimension, which is a categorical symmetry. But last step is not necessary, actually. That is last step only works for finite group. But sometimes if symmetry is not finite group, we can stop here. I think there's a non-degenerate braid fusion category with infinite number of elements or something like that. It's just the higher dimensional physical picture is missing, but we can still, this level still works. So this is the reason we call this a categorical symmetry rather than holographic symmetry, because categorical symmetry is really working at this level. We don't need one higher dimension to make it work. But for finite symmetry, we have this one higher dimensional picture, which we can do using more physical intuition. And but for continuous group, maybe we should stop here. Yeah. So let's just quickly give some idea what is this what is this thing. So the word say that we have an extended operator is a product called the local symmetry operator. So the LSO is a local symmetry operator. It's just product. But however, this local symmetry is too wild. It's hard to do anything with it. I think the most important thing is that introducing this so-called transparent patch operator. So this local symmetry operator, this product only defined on the patch. The patch means no topology. It's like a ball. In one dimension is the length segment, two dimensions disk, three dimensions is the ball. So no topology, trivial topology. But however, we also require that this bulk of this patch operator is invisible, means commute with all the local symmetry operator. As long as this local symmetry operator is inside the patch, far away from boundary. So boundary is observable, but the middle is invisible. So from this point of view, this transparent patch operator creates something on the boundary only from algebra point of view. The bulk is invisible, it looks almost like nothing there. So only create something on the boundary. So in some sense, this is like a fractionalization of the operator, because local symmetry operator is something local. But when you have transparent bulk, transparent patch operator, this local operator became boundary of something. And this boundary is not product of the local operators. But still bulk is invisible. But the invisible bulk somehow say this boundary somehow is connected by this invisible bulk. So this kind of thing exists. So like almost like it's kind of like the example we have in Torah code model. The E particle are created by a pair of E particles are created by a string operator. The bulk of the string is invisible, but we cannot create a single E alone. So there's a fractalization like that. So this is so basically the transparent patch operator kind of describe a fractionalization at the operator algebra level. I think this is crucial, And once you have this fractionalized kind of operator algebra, then the operator algebra of this fractionalized thing is a British fusion category. It became very natural because the fractionalized boundary is something non-trivial, something topological. So that is gave rise to British fusion category. So that's the idea. And so the British fusion category have this data. You have A labeled a different object, and NABC describe the fusion of those onions. And this F symbol we talk about a little bit very quickly, and also this R symbol, but we're using this self statistic, mutual statistic, just try to replace rule of R symbol. So that's basically describe the British fusion category. So we should obtain those data from this transparent patch operator. So how to do that? So the first thing that we have this equivalence relation between transparent patch operator. Two transparent patch operator is equivalent. It only differ by boundary operator. But the boundary, we can multiply some operator on the boundary. We get equivalent patch operator. But the boundary operator has to be a local symmetry operator. We cannot multiply arbitrary operator. Only local symmetry operator can be multiplied to the boundary, and it's still same thing. It's really like a two onion equivalent. It differ by local operators. It's really the same thing like that. And also the string in the middle can move around. So therefore we can multiply the loop of string operator. And this loop string operator we call this non-local operator, which non-local operator is commute with a local operator everywhere. So this whole non-local operator is invisible. And then we can multiply this invisible non-local operator to the transparent patch operator to get another equivalent transparent patch operator. But that means that we move string around. The moving string around is invisible. We don't care where's the string. As long as two ends on the boundary describing onion, but string in the middle is the position is not important. So using this idea, I'm not sure this really works or not, but something like that is necessary to define this. And so the more precise mathematical formulation along this line, I think it's still open question. But along something like that, we hope the equivalence class of this kind of relation would correspond to this onion type, A. So there's an infinite many of transparent partial operator, but they only have finite number of equivalent class. And this is a highly non-trivial step. You know, somehow the representation or something would come out from this. We'll do this. Yeah.
Just technical questions. So when you define patch operator,
Yeah.
this patch operator include only inside the volume. Namely, it doesn't include the operator sitting on the boundary. Patch operator.
The patch operator is just a, you have a lattice model.
Right.
You have a patch, which is like a
Yeah,
disk
so
or segment.
Yeah, this patch should exclude the boundary itself.
Usually they're far away from boundary of the system.
Right.
And so we consider maybe system have no boundary, like a periodic boundary condition.
Uh-huh.
And so the patch, but the patch itself have a boundary.
Patch itself has boundary.
Yeah.
But this boundary is the boundary of.
For my product operator, so I just define the patch, and then there's a product of local operator only for the site inside the patch. But whether include or not include patch boundary is
Not important.
it's not important, because on the lattice, it's not like a continuum space. You have a notion of open set, closed set. The lattice is just a collection of points.
Mhm.
So the patch is just means a collection of lattice points, which are nearby, more or less connected.
Okay.
Yeah.
Maybe.
So the most important thing here is that once you define this, and once this patch operators have an invisible bulk,
Yeah.
the boundary is almost like a fractionalized thing.
So in that line, you just specified all I. I mean,
All
I
products are all
should
in the
be
patch.
far away from the boundary of the patch.
Oh, here, yeah, the boundary would have a patch, yes.
Yeah.
But the boundary again is not. We do not need to be strictly defined.
Mhm.
There's a boundary region, kind of fuzzy region's boundary. As long as I far away from boundary, again, this far away, you can see mathematically should not have far away. What do you mean by far? But physically we can
For
do that.
example, specifically, if I imagine one-dimensional KTF chain,
Yes.
when you define patch operator, do you include the two endpoints?
No, we don't.
I see.
Because the patch is well inside the system.
Okay.
It's near the system boundary is very complicated. We don't touch there.
That's clear.
Yeah,
Then now, when you try to commutate with your patch operator with some local operator,
Yes.
this local operator can be the edge state.
Yes.
Right?
But the patch is inside the box.
Patch should be inside.
Yeah.
should not
Local
be-
operator on the boundary, they just far away.
Right.
They naturally commute.
Uh-huh.
A
Okay.
non-trivial condition is that when the local operator is inside the patch,
Mhm.
then the inside patch may have a non-trivial operator there. They may not commute.
Right. Okay, clear.
Yeah.
Thank you. Yeah.
Yeah, if a local operator is outside the patch, then this is automatically commute. So there's no condition there.
So all these are in just a 2D,
Any dimension.
any dimension?
Yeah, this works in any dimension. Okay. And so then we had to choose a proper representative in each class, such that they can join very nicely. Because whether they can join nicely, ij, jk gave us ik, depend on the boundary. We have to choose a boundary very carefully. So the algebra is simple, they join. And also we need to choose this non-local operator. So these two strings are really on top of each other. And then this product of this patch operator gave us a fusion ring. This is at this level, it's kind of wishful thinking. We don't have a very rigorous general mathematics, but maybe in conformal field theory there's something along this line. But at least we have some examples to show it really works. And there's in conformal field theory there's some kind of conformal net and something like that. And it's along maybe more rigorously defining this kind of structure. And again, using this T patch operator, we can compute F symbol. So actually, this way is you can forget about this fusion space splitting, things like that. This probably is a much more concrete way to compute and define F symbol. It's just that you know this like in one dimension, let's suppose concrete things. We have one dimensional things. The one dimensional segment creating a pair of onion A and A bar on the two end. That's what the transparent patch operator means. They also compute the hopping operator from one end to another end, onion hopping operator. So therefore, so for example, you have a 3 onion A, B, C. You want to fuse them in different way. Basically, we want to using hopping of A and B and to put A, B, C together in one place. This is A, B, C on a one single site. Okay, and there's 2 ways of fusion. So if you fuse AB first, it's like we hop A and B so that AB is sitting on one side. And then we bring C to that side. So all 3 onions in the same site, basically. And then we have different way. We can make a BC on the same side and A last. And the hopping is designed very carefully. So all these 2 processes using exactly the same 3 hopping operator, but they place in different order. So here the below is that it's A hopping, B hopping, C hopping. It's just these 2. This is space-time picture. This operator product picture. And then you can see just different order. And so therefore, the phase difference of these 2 fusion is F symbol. That's defined F symbol. And so therefore, F symbol can be computed from this patch operator. That's a kind of it works at least for abelian. For non-abelian, maybe there's another subtlety. For abelian case, it works. Yes.
Is the right hand side is also sum, or just it's just singleton?
What's this?
Yeah, on the right hand side.
Oh, this side?
Yeah.
The single term. Oh, no, sorry. Thank you. We don't sum of A, B, C. There's no implied summation. It's single term.
I see.
Yeah. This is for abelian case. Actually, F symbol have a sum in general, but that's for non-abelian case. So here I just write down some very simple-minded abelian case. Yeah.
And
yeah.
So you don't need any. I mean, the parentheses. Which one is the first, and so on. Oh, you said this is abelian.
Yeah, the order. No, not abelian. It's A, B, C. This is B, C, A. This operator is not commute. You can say A, B, C, and B, C, A. They associated. The automatic. When you write this way, the operator part always associative. So I hope this appending identity is always satisfied if you construct this way, because it's from operator. Then we can also do this self-statistics. So we can have A, B. Then we can using this 3 hopping, you know, to get to exchange A and B actually. But when you exchange A and B, you cannot compare. And because of the final state, this is AB, the final state is BA. We cannot compare the phase. But when A and B is the same, then we can compare the phase. The initial final state is really the same. And so when A and B is the same, that's only when A and B is the same. So now you can say AAA, they're OA. Then the different order of these 3 operators, but in different place, give us self-statistics. And then this is simple. We can have mutual statistics for A and B. That is A and B, and A and B, just different order, but straddled differently. So this we discussed. When 2 patch operator kind of straddle non-trivially, they may not commute. Non-commutativity means they have mutual statistics. So usually this picture. So that's kind of like an R symbol. So you can see, at least in simple case, those F symbol, R symbol, fusion rule, they're all there. And so in this simple case, we show that this transparent partial operator generate a braid fusion category. And then we just bravely make an extension. You say in general case should work, but exactly how things should work, one need to set up properly. They should have a way to make it work. And so that is kind of a general kind of a mathematical structure for categorical symmetry. So now let's consider some applications. The application of the categorical symmetry is really this topological holographic principle. So we claim that a certain symmetry would have a corresponding categorical symmetry, have a corresponding topological order in a higher dimension. Yeah, you devise a way to compute them. So what that really means? What's the physical meaning of this statement? The physical meaning of the statement is really this: that for any symmetry, there's a topological order in one higher dimension, such that the system with the symmetry are described by boundary of topological order. You know, so the symmetry put a constraint, put a constraint on the behavior of a system. The topological order in the bulk also put a constraint to the dynamic behavior for the boundary. We claim these two constraints are the same. So we can replace symmetry effect by topological order effect. So more precisely is the following statement. There is a one-to-one correspondence between system with a symmetry and the boundary of the topological order. Because when I say system with symmetry, we have many systems. And the boundary topology also have many boundaries. We claim there's a one-to-one correspondence between the system and the boundary, such that the behavior system and the behavior boundary is the same, identical. This is also very tricky. When we say identical, we only mean the correlation function of a local operator is identical, not every operator. Only local correlation function of a local symmetric operator are related to the boundary operator of a topological order. So in some sense, we're trying to say that the boundary operator of a topological order do not include charge operator in the system. Only the symmetric, local symmetric operator in the system correspond to boundary operator in the topological order. So therefore, we need to make some restriction to the system. But this is once I have this make this restriction, the correspondence is identical. But certainly there also should be a correspondence. A local symmetric operator in the system would correspond to certain boundary operator in topological order. Those corresponding operators have a same correlation function. So naively, you can summarize this as the local property is identical. Yeah, but the global sector may not. Yeah, usually system have a more non-trivial global sectors, but the local property is the same. So that is a basic, more precise way to say this this topological holographic principle. Actually, it's very important. So later calculation all use this. Yeah, and so certainly the symmetry here can have a zero symmetry, higher symmetry, anomalous higher symmetry, algebraic higher symmetry, and etc. All these things. And because topological order is very general, actually. There are topological order which we don't know the corresponding symmetry. And we kind of struggle, especially for invertible topological order, whether it corresponds to any symmetry or not. Should we view invertible topological order as some lower dimensional symmetry? We have a trouble to think about that. So this actually invertible topological order is the most unlike symmetry, but non-invertible one very much like symmetry. Yeah. So this is really how we use it. And no. So first application of this holographic principle is this dual equivalent symmetry. That is two symmetry can be equivalent if they have same bulk, if have same categorical symmetry, same bulk topological order. And for example, I will say that in n-dimensional space, the Zn symmetry is equivalent to the Zn to the n-1 symmetry, the higher symmetry. So basically, the phase diagram of Zn symmetry and the phase diagram of of the Zn n-1 symmetry is identical. Yeah. And yeah, there's other things. So let me tell you some little more contribution. So we also have this Z2 cross Z2 symmetry, which can have anomaly in one-dimensional space. So this omega just described this anomaly. So in particular, it's a mixed anomaly. Mixed anomaly described by the 0, 1, 0. This middle one means mixed anomaly. The first index describes anomaly for the single Z2, and the third index describes anomaly of the second Z2, just a self anomaly. And the middle one is a mixed anomaly. It turns out that this Z2 cross Z2 with a mixed anomaly equivalent to Z4. So this is slightly non-trivial result. So therefore, to study Z2 cross Z2 symmetry with mixed anomaly seems difficult. But well, it's just an ordinary Z4 symmetry. Just do Z4 symmetry, you'll get the same thing. Yeah. So that is that's, and certainly this can be generalized for this 4n symmetry. There's a low kind of a recurrence relation, and also if a P is a prime, then this ZP symmetry with all kind of anomaly just divide into some class, I think. So 3 class, one class there's a no anomaly free one is the own class. Anomalous one divide into 2 class, and within each class they just equivalent. And there are also equivalent symmetry between non-abelian symmetry, So this A4 is some alternator group, and this D12 is a dihedral group, and these two are equivalent.
I'm sorry, but
Yeah.
can you remind me what is this upper index is represent?
The subscript is just describing anomaly, and so it's actually I don't know what this means because it's coming from code, and this code is choosing some basis to describe those anomalies. Especially we have many Z2s, and the basic choice is not my code, so I don't know the basic choice. But anyway, it's some anomaly. Just then for example, this the Z2 cross Z2 cross Z2, 3Z2 with certain anomaly, some mixed anomaly, would equivalent to the Q8 or D8, depending on the anomaly type. Actually, these 2 results is known, but here we just get a more equivalence relation. Yes,
And equivalent here means that the corresponding topological orders are the same.
exactly. So the bulk topology order is the same. Yeah. So it's well known that different kind of diagram within theory may describe same topology order, have same topology invariance, although the theory formally looks different, but topology invariance is the same. So those are regarded as equivalent symmetry. And its physical meanings are that their phase diagram, critical point, all the same. But one need to make some mapping. There's some non-trivial mapping, but the basic property is the same. Okay.
Question. In the previous page, G4 case, in the first example, in the previous slide.
Yeah.
So let me
Yeah, this is the simplest example.
Yeah. The first G2 is electric, the second G2 is magnetic. Let me consider 2 plus 1D, some G2 gauge theory, then we have electric and magnetic symmetry, and we know we have mixed anomaly.
Yeah,
So
exactly.
And then what is G4?
No, but
here?
no, this is not electromagnetic. This is really Z2 cross Z2 diagram within theory. Actually, the first Z2 and the second Z2 do not have this interpretation of first Z2 is electric, second Z2 is magnetic. No, we don't. It's a different. Yeah, it's really Z2 cross Z2 diagram within theory. So actually, both Z2 have their own electric charge, have their own magnetic flux. But however, when you have a co-cycle twist, there's a mixing. Yeah. So, but however, this is different from Z2 gauge theory. What you describe as Z2 gauge theory. Z2 gauge theory have a 2 Z2.
Yes.
One is electric, one is magnetic.
Yes.
And the Z2 gauge theory is never Z2 cross Z2 diagram within theory. They are always different.
Yes.
And but this is really Z2 cross Z2 diagram within theory. There's something, yeah. But that's a very good question, because at the beginning we thought this electromagnetic relation kind of like anomaly, but not quite. This diagram theory is anomaly.
So it's not easy to understand what is G4.
No,
So
it's a
physically
this is really diagram theory. No, Z4 is just ordinary anomaly free symmetry, Z4 symmetry. And we try to say that Z4 symmetry and the Z2 cross Z2 symmetry with the mixed anomaly is the same. It's equivalent symmetry. But then it's really we did not go into this very detailed. What is anomaly? What is SPT? How they are related? Yeah, maybe if you have 2 more lectures, I probably can cover that. That's also a big story. Okay, so this is basically a part which is about this viewing topological symmetry as a shadow of a topological order. So next we'll do this more let me see more. Oh, okay. Yeah, the more example, and this may be more practical application. Yes.
So I think this categorical symmetry, deals with ordinal symmetry and its dual symmetry,
Yeah.
equal fitting, right?
Yeah.
So, for example, if we consider 1+1 the Ising model,
Yes.
then there's Kramers-Wanier duality,
Yeah, exactly.
which are sorted equally.
Yes.
But it also has boson-fermion duality to
Yeah.
fermions, right? So,
Yes.
do we have? Can we also see the appearance of boson-fermion duality in this picture?
Yeah, I don't know this it's a little bit difficult to see from upper algebra point of view. It's the same. Actually, indeed, if you can using this the boundary. Let me see what is whether there's a okay. Let me put it this way. In the box theory, have the EM exchange duality.
Mhm.
This EM exchange duality is correspond to this Kramer-Wanier, and I think that's all. The boson-fermion. Yeah, I don't know whether have a natural interpretation here, because whether that's just formalism have something, or whether there's real content.
So there may be some way to realize the boundary, with fermions starting from the boundary.
Yeah, the point is that the different duality correspond adding different choice of boundary, but there's only 2 boundary, either E condensed or M condensed, and E plus M do not condense. But what I try to say is there can be other things, because here I did not talk about the fermionic theory. And if you talk about the so-called fermionic theory, maybe there's some other formulation which make it so you can address how bosonic theory is due to fermionic theory. Because here we only talk about the bosonic theory. We did not formulate the fermionic theory. So I think maybe that's the reason I have difficulty to answer your question. If you formulate the fermionic theory, maybe there's some reason, some case bosonic theory can be due to fermionic theory in some sense. Yeah. But I need to formulate the fermionic theory first.
Follow-up question. So let me ask you this question in this way. Suppose I start from fully fermionic G2 gauge theory instead of bosonic G2 gauge theory.
Fermionic G2. Oh, yeah.
Fully fermionic toric code.
Yes.
Then I go to some boundary H. So can you?
It's the same. The
say?
fermionic G2 gauge theory in 2+1 dimension, same as the bosonic gauge theory in 2+1 dimension. They are same topology order. The reason is that because fermion carry gauge charge, the gauge in one object have the same problem, same property. So the Z2 gauge theory coupled to fermion matter and Z2 gauge theory coupled to boson matter is equivalent, the same thing.
Well,
so that's why we do not even distinguish them. We call them Z2 gauge theory.
I'm somewhat confused. So if I consider some Maxwell theory, fully bosonic Maxwell and For remaining Maxwell.
In 3 dimensions, they're different. In 2 dimensions, 2 plus 1 dimension is the same.
I see.
Yeah. Indeed, you're totally right. In 3 dimensions, the fermatic Z2 gauge theory in 3 plus 1 dimension have 2 versions. One is the charge is boson, another version
Yeah.
charge is fermion. Yeah, probably I will talk about that tomorrow in the math department. Yeah, but this is very important.
I see.
In 2 plus 1 dimension, the same theory. Okay, so as a last, maybe most important application of categorical symmetry is as a beginning, as I mentioned in the first lecture. Our dream is that using categorical symmetry to systematically understand, even classify, if you really push all the gap and the gapless theory, both in a unified fashion. Okay. So so how that be possible? You know, so the point is that we need to have a data to describe the categorical symmetry, or maybe we need data to describe bulk topological order. This way is important. Thinking is important because of the topological order is the bulk topological order is a much more general way to look at the symmetry. If you're using the ordinary point of view to look at symmetry, this program will fail because here we're using emergent symmetry at low energy to characterize, classify low energy physics. But the emergent symmetry is very, very rich. It's much richer than the ordinary symmetry, the ordinary higher symmetry, and such. But somehow this topological in one higher dimension also became kind of universal, maybe covering description. So maybe there's some chance, maybe all the emergent symmetry is covered in this formalism, using topological in the bulk to describe symmetry. That probably can cover all the possible emergent symmetry. So this program may have some chance to succeed. But this part we already done. You know, we described that's the first few lectures. We described topological very carefully, and we understand what kind of data to describe to characterize topological order in low dimension, not in high dimension. Then we also need the data to describe 1 dimension the gapless states or in any dimension. But in 1 plus 3 dimension, we have answer. In higher dimension, there's trouble. Then we just how these 2 data are related. Then we have a program based on something like that. Yes.
So here, do we consider the local symmetries too?
What's the local symmetry? I mean,
So in the previous slides, we talked about like local symmetry operators and so on. Like in the lower dimensional series, do I consider the local symmetries?
Yeah, basically the you know we'll have a yeah. Let me put it this way. Okay, I don't know exactly the question, but when we consider low energy effective theory,
Yes.
our so-called local symmetric operator actually should be also called the low energy operator.
Okay.
It's a somehow there's a low energy subspace. It acts within low energy subspace. That's how emergent symmetry may come up. Because when you have a lattice model even without symmetry, then the local operator can be arbitrary, no symmetry. But once you have low energy subspace, then suddenly you using low energy to select a subset operator. So those subset operators only act on the within low energy subspace, have non-trivial algebra.
Okay.
And that is the emergent symmetry. So indeed here the symmetry are really using emergent symmetry in this way. And so that means so-called low energy operator. This local symmetric operator become a local low energy operator, which have non-trivial algebra. And this is a formal way to derive low energy effective emergent symmetry by requiring the operator only act with low energy subspace.
So I think I should have asked this way, like global on-site symmetries, is it the symmetries I'm considering, or like so in certain cases, like
we don't. Okay, the symmetry here, when you say categorical symmetry or symmetry here really means either zero symmetry where act everywhere, or higher symmetry act on some manifold.
I see.
Or maybe algebraic higher symmetry act on some manifold, but the algebra is more complicated.
Okay.
So I'm really thinking along this, yes.
Yeah,
including higher symmetry, yes. But in 1 plus 1 dimension, we don't have room to have a higher symmetry. We don't have a real symmetry. But in higher dimension, yes, there is a higher symmetry. Yes.
By the way, so maybe in all these cases, what you have in mind is at the boundary there is no symmetry, while in the bulk you do have some emergent symmetry.
Yeah, actually in some flavor. Okay, at the beginning, we do have boundary, we have symmetry. Then this categorical symmetry is a way to deal with the boundary symmetry in a way not to have symmetry. Means I want to remove the symmetry. I want to consider a system without symmetry. But we can still describe a symmetry effect by saying my system without symmetry actually is a bulk theory. Then the bulk topological order have a constraint on the boundary dynamics, which have a same effect as a symmetry directly constrain the boundary dynamics. And so when you have this holographic picture, the whole picture have no symmetry, have no global symmetry.
So I would like to ask you that suppose we do have some symmetry
At the boundary.
at the boundary.
Yes.
And then is there any general rule to lift it to the bulk?
Yes. That is then we view this boundary system as this is our system with the symmetry as a boundary of a bulk. But this bulk is a product state with the symmetry.
But the symmetry is the same or not?
It's the same, the same group. Yeah. Then you gauge the bulk theory and the boundary together. After gauging, there's no symmetry anymore. Then you have topological order, then the topological describing the boundaries. We gauge both boundary and the bulk symmetry. Actually, you gauge the bulk. When you gauge the bulk, there's no way to not gauge the boundary. They are connected.
Global symmetry on the bulk, and do you
Yeah,
have
we
a
don't
similar
play that
relation
game.
to the ADS shift?
Yeah.
Like,
You can have global symmetry in the bulk.
oh,
But
you
that's
can have
a
that.
more situation. I did not consider that situation. And what I don't need to, because our strategy is that we have a system with a symmetry. We want to use another system without symmetry to simulate a system with a symmetry. This is possible, but my other system have a bulk, and the bulk have a topological order. So therefore, our original system with symmetry is simulated by the symmetry by one higher dimensional system, and so we play this game. The certain may say, why you do this? You know, this is like makes things very complicated. But actually, you'll see a lot of things when you play this game. You see more. Actually, I feel this is very, very important. We should, yeah, maybe let's just say all the way of symmetry are all wrong. Maybe I really that's not too much. It's not wrong, but at least it's not convenient angle. And so this holograph picture is a much more convenient angle to look at the symmetry. So certainly we need a topological order described by ST matrix. And here just actually not review. The ST matrix can be actually computed from the wave function overlap. You know, on the torus, you have a degenerate wave function. And S matrix actually is a wave function, the degenerate wave function labeled by alpha. And then we can do 90-degree rotation and consider wave function overlap. And our system have no 90-degree rotation symmetry. When you do this 90-degree rotation, it's not symmetrical transformation. The overlap is tiny. Actually, it's a very, very small. It's area just coherence length. So it's almost no overlap. But however, if you do things more carefully, there's a very tiny overlap. That's the leading term. Area term proportional area. Then the subleading term is universal. Like entanglement entropy, which I did not cover here. The leading term is not universal, it's very tiny, but if you zoom in, the subleading term part is a S matrix, just wave function overlap.
Sum or product? S and there.
Oh, this is S alpha beta is a fixed index. So here alpha beta is fixed. Just two-way function, rotate one by 90 degrees, then have to overlap. So then we can do some more weird. So this is like a shear transformation from this to this. You know, this x plus y, but this y is not changed. So this is like a shear deformation, not like a 90-degree rotation. And you can also do this. Anyway, it's not symmetry. Again, have very tiny overlap. But then the constant part is universal. And that's the T matrix. And we test this by this natural numeric calculation. Indeed, we have this picture. So to understand this relation between the bulk topological order data, which is ST matrix, and the boundary theory, then we need to have a little bit of understanding where this degenerate ground state come from. What is the picture for the degenerate ground state on the torus? So here we think of our torus is a space is torus. Then we think of the space-time is a solid torus, which is so the past history is the inside the torus. So this blue one is a solid torus is space-time, so the radial direction time. And usually if you evolve evolve our system, we get a particular state on the boundary. We get a particular state on the boundary, which we call the identity state. To get other degenerate boundary ground state, we have to insert anion. So this is the anion word line in the bulk. So basically, we create a pair of anion, then wrap the anion around in one direction. And when you have an anion word line in the past history, you know, at the current time there's no anion, but somehow this anion word line in the past history change the ground state to another ground state. So therefore, the degenerate ground state of torus actually are labeled by the anion type. There's always a trivial type of anion, which is the original ground state, but for different non-trivial type, you have anion type. So therefore, you can label the ground state using anion type. Indeed, the degeneracy is equal to anion type. You have 4 anion type, then there's 4 degeneracy. Now it's under the modular transformation, this you know, the previous we say under modular transformation we had the ST matrix, so we can imagine under modular transformation, this surface degenerate ground state will transform using like ST matrix.
So my elementary question.
Yeah.
In the previous page, X and Y transformation, it does not look like modular space. It is real torus.
It's real torus. But the transformation, this kind of transformation is a modular transformation. It's a mapping from square to this something. You know, modular transformation have 2 versions. One is SL2Z as superhedo matrix. Another version actually is as a mapping torus to itself. So XY is coordinate label torus. This XY to Y minus X is a one mapping from torus to itself. And this XY to X plus YY is another mapping for torus to itself. And this actually the modular transformation is describing this kind of transformation. The mapping torus to itself is a modular transformation. Yeah, it happened to be group happened to be SL2Z. Yeah, the generator group is SL2Z.
Where this alpha index runs?
It's a degenerate ground state. You know, on the torus, there are several degenerate ground states, so like 4 degeneracy. Then alpha beta would have range from 1 to 4. Yeah, it's just labeled degeneracy. But then here, actually, this label should be anion type. It's the same. The degeneracy coming from different anion type. Yeah.
So by this bold line in the
By this
figure,
picture. Yeah.
yeah, that is the
Yeah, different anion tunneling past history give rise to different degenerate ground state on the torus. And so there's a correspondence between anion type and the degeneracy.
I'm sorry, but I didn't understand the meaning. So is it inserting the Wilson line operator or?
Yeah.
Okay, thank you.
But like it's more general, you without gauge theory, they're similar thing. Yeah. Yeah, it is for gauge theory is this one is inserting Wilson line operator. and also existing two-of the line operator. So all those things. So it's natural to think that if you make a transformation in the space doing this modular transformation in the space, the ground state will map. Yeah. And for example, you can see this tunneling of Anyang is in the y direction. You can imagine we fill the cylinder differently. So here we fill the cylinder where y is non-contractible loop, but x is contractible. There's another way to fill the solid torus, which make a y contractible, but x is non-contractible direction. Then you can insert Anyang line in the x direction rather than y direction. And that gives you another basis of this degenerate ground state. These two bases are related by this asymmetric 90-degree rotation. So it's kind of game we play like that. So we can try to argue, yeah, estimate under modular transformation, this general ground state also form a representation of SL2Z, which is general by ST. Again, yeah, this is not duration. There's a lot of jump, but I try to draw some picture, make it more reasonable. Then let's go to the one dimension. So far it's still just a two-dimensional picture. Yes.
I have a question. So when you think about filling the torus, there's a choice of which cycle is contractible in the filling, and presumably that changes under SNT. So is that so you do keep track of this. It's not just the torus; it's the torus with a filling, and your SNT transformations act on that full solid torus.
No, SNT transformation actually act on the degenerate ground state.
Okay.
So formally, we have ground state have degenerate subspace. You can have some unit transformations that act on that. And here I'll try to say that certainly this unit transformation depends on choice of basis. So there's for the same degenerate ground subspace, there's two ways to build the basis associated to Anyang type. And this way that we make an X contractible and using Anyang type in Y direction to determine the basis. And for the same degenerate subspace, you can think they come from different time of solution, and then make a Y contractible using Anyang along X direction to build the basis. And these two bases span the same degenerate subspace, but they are different bases, and they are related by this S matrix. So that is the way to understand why modular transformation, enter here. So in one dimension, how do we describe a data for one-dimensional system? Well, partition function. And here we define more general partition function. Partition function depends on tau, which is shape of space-time. So tau describe shape of space-time. It's kind of like this. Tau is you can say, if you say this space vector is a 1, there's a complex number is this vector. So that depends on the shape of this space-time. So you can think this is different tau have different shape. Then partition function may depend on shape of space-time. And in condensed matter, we can define this as the following. If you have system 1D system with size L, the ring size L, then the partition function usually just a Hamiltonian with a beta. Okay. But this beta is a parameter that's an imaginary part of tau times system size times the inverse velocity. So this is our beta temperature. And then we also, but the real part of tau is just a real part of tau times L is translation. So that means usually partition function, we just do partition function. But here we do partition function. Before we take a trace, we translate, then we take a trace. So this additional twist by translation describe a real part of tau. And so that gives us space-time. It's a slanted space-time because this additional translation. And so this partition function is a data for 1 plus 1D system. So we want to relate the data of a topological order ST matrix with this data tau, the Z tau partition function. And usually in 1 plus 1D system, this partition function have modular invariance. Okay. But however, this is so-called real Euro situation is for pure 1D system without bulk. And this we call the system without gravitational anomaly. When the system is defined without bulk, it's anomaly free. So our intuition here is that this modular invariant condition is anomaly free condition. Yeah. And we have a anomaly because we are considered boundary with bulk topology order. This 1 plus 1D system is supposed to be anomalous. Then the anomalous, the point that anomalous 1 plus 1D system have a multi-component partition function. The partition function have many components. That's the key. Why it have many components? Because so this axis is space and the vertical direction is time. And then this blue one is a bulk. We can insert onion word line in the middle, do not touching the boundary. So like inserting onion word line in the bulk, the boundary is not affected. But inserting different onion, the boundary are in different sectors. In conformal field theory, actually inserting onion in the bulk is like in the boundary, you're inserting the topological defect line. These are the same thing. So that gives you a different sector. So therefore this we have a partition function have many components, and this component labeled by onion type. If you compare this picture and the previous picture, it's just exchanging y and t. So now you can see that this different component partition function is related to the different degenerate ground state in a certain basis. And so I don't derive. So this is the key. So this is we have a modular covariant. So this multi-component partition function is not modular invariant, the modular covariant. Under this modular transformation, the partition function change by some unitary matrix. And this unitary matrix is exactly the same unitary matrix described in the bulk topology order. And this may be another key point. That is the bulk topology order and anomalous boundary partition function have this very direct relation, but using modular transformation. And that's it. So in 1 plus dimension, this may be the program. That is the main idea. Just using this, we can derive the boundary theory from the bulk, just from this. Yes.
Okay, for string theory case, we are summing over. So basically, we are doing quantum gravity. So we have a modular invariance is obvious, but here we are doing just a given fixed metric, right?
Yeah, fixed symmetry,
So
fixed topology.
nevertheless, where the intuition of the modular invariance is coming from? Or
It's coming from
is
here. That's
coming
the
from-
wave function transform like this. But the wave function is something on the surface. And the partition function also something on the surface. So that is the intuition. We say so the partition function should transform like a wave function, which is modular covariant.
So is this just the a priori it should be like that, or you just calculate and you just it turns out to be?
No, yeah, we have some calculation, and you know, some universal model, you can show that, yeah. So actually, these two things almost the same in the sense, you know, this boundary wave function is just you fix the index. You know, this a function for index on the surface. That's a boundary wave function. The partition function is just put some boundary condition. So all the index taking same value or some value, you get a partition function. So these two are kind of similar. And yeah, so there's some duration, there's some idea, but yeah, I don't know whether duration is rigorous or not. It's so to me, I just feel this cartoon picture is convincing enough because of the, okay, let me put it this way. I believe that this multi-component partition function would transform covariant and modular transformation. And what is a ST matrix? This is very natural to be bulk.
Because I would say that this is previous one. This
Yeah.
The requirement of this wave function
Yes.
has a nice modular property.
Yes.
It's a really non-trivial thing, and
Okay.
can you give me some
Yeah.
hint
Let
why
me
it
say this.
should be so?
Here, the overlap between two wave functions. So what is the partition function? The partition function is overlap of this wave function with the product state. That is the boundary partition function. Because the outside of this cylinder, outside this cylinder is a product state. You pick a product state outside cylinder. The partition function actually is overlap of the surface of wave function with this product state. And and this part is actually energy density. And this part is non-trivial topological part. So basically, if a wave function transforms like this, the product state do not transform non-trivially under modular transformation. So this overlap between the wave function and the product state would transform in a similar way as ST matrix.
Right. Even before we discussed the partition function, to me, the fact that ground state wave function is transforming like that is again a little bit non-trivial.
Yeah, it's non-trivial. But this one, remember, we described this before, not using wave function overlap, but using this, we changing the space continuously using non-abelian barrier phase. And this way, this wave function is another way to compute this ST matrix. And but not using non-abelian barrier phase. Because when you're twisting the system, the ground wave function also twists around. There's a vector bundle non-abelian barrier phase described as ST matrix.
So why it always follows area law?
Because of the overlap is very tiny, because these two wave functions are locally different. And so each local parts give you some reduction factor. The number of local parts proportional to area. So therefore, the total magnitude overlap is very tiny. It's exponentially corresponding area. But however, this area is not important, non-universal. If you remove that, we claim the second part, the constant part, is universal. It's this ST matrix.
So this is a proved one or is conjectural thing?
Conjectured, and we have numerical calculation. Yeah, nothing is proved here.
I see.
Yeah, in some cases, when you have exact solid model, you can prove this. In general, as this general statement, there's no proof. Yeah.
So, if we have topological order on the bulk, then the partition function on the boundary should covariantly transform.
Yeah.
But what if we have primitive fermion topological order on the bulk? Then we cannot find SNT matrix which correspond to the mapping class group.
Yeah, it's very important that everything here is bosonic. Nothing is about fermionic.
Then
if a bulk is fermionic, it doesn't work. So actually, that means if a bulk is fermionic, that means you did not gauge all the symmetry. So, for example, the boundary have some symmetry. Then you say the bulk is a product state with that symmetry. When you gauge the symmetry, you can gauge part of the symmetry. If you gauge part of the symmetry, that's the situation you described.
So
the bulk SET don't work.
Okay.
But if you gauge all the symmetry, including the fermion parity symmetry, the bulk became a bosonic topology order. Then you have non-degenerate modular tensor category. Then that will work. Very important. But actually, that's a very good point. So you can think a generalization. I think if you do not gauge all the symmetry, it still works in a certain way. But you have to modify those conditions should be modified. And that should be useful, actually. And here, just because as the first round, we just describe a simple situation, extreme situation, we gauge everything. You can gauge partial symmetry and then to see how, in that case, how one should formulate this kind of idea. The idea to the similar, but there should be modification. Yeah, very, very good question. That could be some research direction. Yeah. So,
Sorry, I have a little question.
Yeah.
Do you think this picture can be extended to, I mean, higher dimensional situation?
yeah, we intend to so I just chose a way of describing the theory in such that this description is naturally generalized to higher dimension.
So,
Because this ST matrix is really a mapping class group which work in any dimension.
So in higher dimension, there will be higher dimensional anyons which can be inserted in the
Yes, there's a loop and the strings and yeah.
I guess, do you think, I mean, we need to, I mean, provide additional data to S&P matrices?
Maybe. Even in two dimension, the matrix is not full description for modular tensor category. So therefore, therefore, this is partial theory. And so how one include additional information? That's a big question, you know. And yeah, even in 2+1 dimension to 1+1 boundary, there are issues. Yeah. There are things that beyond this estimate module data. Yeah, this one need to do something more here. So again, you know, this is a program and a direction. And at the moment, it kind of initial stage of this program. And there's a lot of subtlety need to be completed.
How important is it to be only thinking about orientable manifolds? I mean, if you think of the toy examples of quantum Hall states, then you have a magnetic.
Yeah, you have a very good question. So,
but
you can see
lattice
here.
theories, I would think.
Here we only consider this the internal symmetry. I did not consider the space-time symmetry. That's yet another direction. How one incorporates space-time picture in this program. I don't know. Yeah, this is that one. I have less clue. Yeah. Yeah, but that's actually should be very important. Yeah.
But when you said you have these numerics, do you have? I mean, the naive thing I would think is to think about some Laughlin wave functions. Do you have any things where you can define the wave functions on unoriented manifolds or no?
No, as an example we have is have time symmetry. So actually, the calculation we do simulation is really for the Tor code model, but with modification, when add additional terms, become no longer soluble. But there is a soluble limit, you can check your results. And but even in non-soluble limit, you can see the transition, you know, and so to see this kind of thing. But however, the wave function in the whole deformation wave function have time reversal invariant. But how to extract this time? We did not probe this additional symmetry. You can see we only gauge internal symmetry. We don't gauge the time reversal symmetry, and we don't know how to gauge them. So that's really interesting. So almost like a gravity, you know. Here we only gauge internal symmetry, or something like a topological order gauge theory. There's no space-time symmetry. We don't gauge that. In some sense, you can say there's no gravity. But with the gravity, with dynamic, so when you gauge that, should be dynamical gravity. Because here, all the internal symmetry become dynamical gauge theory. It's not semi-classical gauge theory. So that makes things really interesting. I don't know for the space-time symmetry, you gauge that becomes dynamical, almost like you're doing quantum gravity. So that's an open question naturally. Yeah, very, very interesting. Yeah. Okay, so yeah, that's it. Actually, from here, you know, rest is just tricks. You know, the physical picture are really just here. All the physical picture, although you know it's incomplete. But however, as a practice, this condition, although incomplete, is very restraining. So almost fulfill our needs, and in practically, we don't need more. But certainly, when you do very complicated system, maybe we need more. But for simple system, we don't need more. This is enough, really. So now is how to solve this equation, you know, and so it's I want to emphasize that solving this kind of equation actually is a number theoretical method. Usually when you compute a critical theory, you do epsilon expansion, Lagrange expansion, or something. It's like a Feynman diagram method, like this way. But here is a number theoretical method. The reason I emphasize this about because when you compute this critical exponent, critical theory, you compute the critical exponent, which is a rational number in 1+1 dimension. Usually it's rational number, okay. But using epsilon expansion, Lagrange expansion to compute a rational number seems very strange, yeah. And so if you can compute this number directly, would be nice, yeah. So this so-called number theoretical method is a kind of in that spirit, try to compute that directly. So here I want to say one thing that the partition function actually is a polynomial of this parameter. Because partition function coming from each energy level, the contribution from each energy level have a weight. So this kind of weight from each energy level and the momentum level. And their contribution is 1, either 1 or 0, means no level there. So therefore, this partition function is a polynomial of this Q and the Q bar with an integer coefficient. To be more precise, it is non-negative integer coefficient. Yeah, there is some little bit of shift of overall shift of ground energy. Let's don't worry about that. That's a scaling dimension central charge. But the main part is a polynomial with a non-negative integer coefficient. So now we come to this mystery that this is pretty much constrained polynomial under such this condition. So it's highly constrained, and we don't know how to use those conditions. The so-called modular bootstrap do not use this condition. They only use a non-negative condition, not using non-negative integer condition. You're actually missing most of the condition. But the modular bootstrap already is a big industry, as people say, it's very effective. You can see how much we miss. Even though we miss so much, it's still big progress. So I couldn't imagine if you can find a way to use non-negative integer condition. Yeah, this is very, very highly constrained. But this certainly is a very open question. We don't know how to do this. And actually, people here actually working in this direction. Maybe one can find out this, whether there's some way, more number theoretical flavor of approach can really solve the critical theory problem. So I'm kind of promoting this kind of approach. And so for the generalized this modular bootstrap, and we just using covariant condition. So it's not invariant, we're just using covariant condition. And actually, we don't know how to do it. Indeed, this is a big problem. So actually, so I should stop here. I cannot do anything, so nothing, no new results. But fortunately, in the last 30 years, we have developed a lot of experience in conformal field theory. So we have a library of conformal characters, which transform under some known ST matrix. Yeah. So we construct a lot of example conformal theories as a big library of that. So then we just making guess. We say, okay, we just guess this polynomial using this library conformal character, just putting this chi bar together. They're like a tensor product of these two characters. It's a tensor product of SL2 determination. And then we put in some inner triangle, some coefficient to reduce this SL2 determination of conformal field theory into the proper one, because we need a particular SL2 determination described by the TM and SM. But what we have is a tensor product of TS, TCT, CFT, and SCFT, a tensor product of two of this. Then we want to combine do some projection to go into this the required one. So therefore, if you do this, we find that there's a non-negative integer coefficient here to make this into a proper SL2Z representation. And so our input is this conformal field theory module transformation and also topological order module transformation. That's our input. Then at the output is that this intertwined coefficient, this coefficient here, non-negative integer coefficient. Then once you that you have actually how you can construct this module invariant partition function. So we have a computer code to do this. And the problem is that we are not computing anything, we're just guessing. You know, we have to input this conformal field theory SIT matrix. And most time when you input them, you find there is no solution. So then that's also as a physicist, that's fine. Then that's kind of fun. Now we need some physical intuition to say which conformal field theory match with this topological order. Some intuition, and making some educated guess, and then try to come up with some solution. Many times my intuition not so good, so I just don't get any solution. But sometimes I'm get lucky, you get a solution. Certainly, this is not the ideal situation, and we hope there's a better understanding. We have a more systematic program to compute this topological order.
So could you remind me what is the difference between S and SM?
The SM at TM emphasizing this is module transformation for the bulk topological order.
Without M means?
You know, previously I when I write this ST, here add M. You know, sometimes I don't add M. Like here, this ST I did not add M. They supposed to have M.
So that S without M is for the ground state.
No. With or without M, they are all for topological order. I want to distinguish with there's ST matrix for conformal field theory, which are CFT. Those are ST matrix for the conformal character for conformal field theory. That's different ST matrix. You know, when you have conformal field theory, you have this modular transformation given by the conformal character.
So this I mean the GIs also count the only the ground state property?
Yeah, ZI is a ground state property. It's a boundary ground state property. So our boundary CFT property. So we want to compute, our goal is to compute the ZI, which satisfies this condition given by SM and TM. But however, we know the conformal character satisfies a different condition, but given by T CFT and S CFT. So therefore, this conformal character Z chi is not the Z. But however, we can combine using those conformal character to construct a Z like this. The chi transform as a S CFT T CFT, but the Z transform as SM TM. They are different.
Yeah, I wasn't very sure whether you by inserting these version lines or type I anion, whether they belong to the kind of ground state or excited state.
They actually okay. So this partition function describe the conformal field on the boundary, which can be gapless. So that include the ground state and the low lying excitation. Because partition function depend on both depend on all the low energy excitation. So the information of all the low energy excitation is inside this partition function. So it's a low energy dynamical property.
Yeah, but that is not the really, I guess, coming from ground state wave function, right?
Yes. Yeah, that is the amazing thing. So when you do the weak rotation, the ground state, now the space is two-dimensional space. We have a ground state wave function in two-dimensional ground state wave function. The partition function is a partition function with one-dimensional ring, but it's a dependent space-time. The partition function again is two-dimensional property of a xt space-time. And this, but that includes excited state. So exact state on the ring would map into the ground state on this XY space. So exact state in the space-time of xt is same as the ground state of xy. So there's a weak rotation. We rotate the y direction in the ground state. In the two-dimensional ground state, we have x, y. We map y, rotate the y into t direction. Then this ground state wave function would encode dynamic property of one-dimensional lower system. Yeah, that is what this picture. This you can this y became t here.
Follow question. So what is the partition function GI? What is the transformation property against TCFT and SCFT? It's modular invariant with respect.
They
to
don't transform because the z we require z just transform according to this topological order modular matrix.
So
It's a mathematical trick to using some conformal character to obtain the partition function transform properly.
is there a way to derive this TCFT, SCFT from?
No, there's a way, but it's a 30 years of work. I mean, 40 years of work.
I mean,
There's a lot of individual CFT, and the computation of each of them is non-trivial.
from bulk.
No, it's a different computation. You can see this one is the mathematics, no physics. And this chi just a polynomial of q's. And the people construct those q, which happen to from a known representation. So no physics, it's just a we know a library of those function of tau, which transform under all kind of TCFT and SCFT. Then we're using those knowledge, not just mathematical knowledge, no physics, then to construct the ZI, which transform under given this SMTM. Yeah. So we don't need to even know the conformal filter. We just need to know some function transform like this. And we do have a library of those functions transform under a library of SCFT and TCFT.
Frankly speaking, maybe I don't quite catch the bulk boundary correspondence here. The precise meaning of bulk boundary correspondence here.
The precise boundary is here. ZI is a boundary partition function. SMTM is bulk. That's how the boundary bulk are related. You know, SMTM is a bulk data, bulk topological data that determine the boundary property. That's a partition function. Just it's one line. That's everything. Yeah, this is the whole thing. And the next transformation is just some trick to solve it, to find a solution, to find a ZI. We satisfy this equation. Just mathematical tricks. Yeah, and happen to be in last 30, 40 years, we have a lot of example of this chi function with known transformation. Then we just combine this. This become group theory. The tensor product of two representation after some projection can give rise to another representation. And we want a particular representation given by this SMTM. That's what we want. We can start with a different representation, doing a tensor product and do some projection and obtain this particular representation. So this is what we do. So this pair is tensor product. This coefficient is really, because the tensor product contains a lot of other representation. You want to project other representation out. Only select representation which forming this SMTM representation of SL2Z.
Then this SMTM are the basic data we need to provide, or
yes, that's categorical symmetry, the bulk topology. You can see when you compute when you have a symmetry, we compute the bulk topology order. What do you mean by compute the bulk topology order? Compute the bulk topology is compute SMTM. I see.
But can we calculate this SMTM from something else?
Yes, that's a previous slide. When we do the module tensor category, we have this R. We talk about the A, NABC, this F symbol, R symbol. From those data, you can compute SMTM. Yeah.
So,
Yeah, indeed, that's a very good question. Yeah.
so in usual CFT, so modular invariance means the partition function is invariant under the modular transformation SCFT and TCFT.
Yeah, that's a modular invariant.
Yeah, against SCFT and TCFT. TCFT.
No. It's just an invariant. There's no S. It's just the function. It's just that. But you can construct the modular invariant partition function using that. You know, by choosing this properly, there maybe you get the modular invariant. You know, there's a way to operate a modular invariant partition function using this conformal character. That's what people do in Euro conformal field theory.
Yeah.
Using conformal character to construct modular invariant partition
Yeah,
function.
but they are TCFT and SCFT the data. No.
No, it's a, it's modular invariant. It's a, when you in your construction, yeah, these are TCFT and SCFT here. But once you get the modular invariant partition function, just a modular invariant. Inside it, you have TCFT, SCFT, but as a partition function, you get the modular invariant partition function. So the TCFT, SCFT is there, and so in some sense, this is very much like this Euro conformal field theory. And this coefficient is called the gluing condition. In the Euro conformal field, people want to glue them together to form modular invariant partition function. Sometimes this gluing condition can be non-unique, can be several of them. And here we do the same thing. We have gluing condition, but we do not aim to get the modular invariant partition function. We want to get the modular covariant partition function which transform in a certain way. So it's kind of similar to the standard approach conformal field theory, just we're changing from modular invariant to modular covariant. Yeah, that's so it's very in line in the earlier study.
Hello, I have a question.
Yes.
I think that your bug boundary correspondence is similar to using the 3+1 dimension U1 gauge theory. In this theory, we can also have the S operation and T operation, and then this operation can induce a 2+1 dimension.
That's why I don't know. Yeah, because in first 3+1 dimension U1 gauge theory is gapless.
Yeah, that's one.
So already outside my discussion.
So maybe I saw.
And that ST transformation is a different ST. It happens to be modular, but it's very different meaning.
Yeah. So my question is whether we can have some lattice realization to see this emergence of the duality wave. Because I say that the bug boundary correspondence is very similar.
The duality of symmetry. You mean?
I mean, say, okay, in the Witten's paper, they show that you can use the 3+1 dimension U1 gauge theory, and you use the T and S operation to induce the 2+1 dimension duality wave. This is their paper's claim.
Yeah.
And they show that. But now I think that in bug data, now you define it is from the T and S matrix, which correspond to the U1 gauge theory. And then
if U1 gauge theory have a transform, I don't know. Yeah.
Yeah, it's so it's what I want to ask. I don't make sure.
I think there's we have this there's a duality. Well, so actually this I'm talking about the duality symmetry. It's the same thing. The two symmetry are equivalent if the bulk is the same.
Yeah.
So that's in the same spirit. Of this using bulk to determine duality web. It's actually all this table you can view as some kind of duality web.
Yeah. Sure. So I just want to say whether we have some lattice realization for the Witten's duality wave. Because language is similar.
Yeah, language is similar. The thing that the symmetry, because U1 symmetry, so the formalism here don't quite apply. So I don't know how. Maybe this possibility that the U1 symmetry is not gauged, and but you only gauge other symmetries. And I don't know. Yeah, so this is how one apply to there. This issue. What is the bulk topology order? And basically it should be matching anomaly. Basically, the duality edge is matching anomaly, and so anomaly is same then the same. Yeah.
Yeah. Thank you.
Okay. Yeah. Okay. So here, so the key is that we want to find this combination. That's a pairing these two together. Oh, I think do you want a 5 minutes break? I forgot. Okay, yeah, maybe, yeah, if you want to go to restroom, just go. So, yeah, become a little rush, and you can see this is 8 to the 34.
So if everything is from conformal block,
Yeah, everything from conformal.
then how conformal is really not
Professor Sangjin, Professor
What?
Shah. So you want to break 5 minutes?
Maybe
Or
not.
continue.
I'd say, yeah. I just say if you need a break, just feel free. I need to continue. I had to finish as much. Yeah. What's your question? Yeah.
So maybe all this prescription, this you get the I mean the SMT, SM and TM
Yes.
from the bulk, and then construct the conformal field theory out of there.
Yeah.
And that is probably for maybe gapless case,
Yes.
but the similar prescription exists for capped case
Yes.
also?
Yeah, I'm going to talk about that. Just the next slide. So here is that so this coefficient is very important. It describes how we construct the boundary partition function, and how this boundary partition function are associated with certain kind of conformal block or conformal field theory. And so this coefficient Nijk is just describing that. Now I want to introduce AI, which basically is a Ni and 1,1 component. The 1,1 component is actually, conformal character also have a character which is like unit, like a current algebra unit, not like a non-trivial sector. And so there's a canonical unit sector which is labeled by 1. Okay. So this like this sector in terms of conformal field theory, this alpha is labeled primary field, and the 1 means correspond to the identity primary field. So this that's something that sector. Now other alpha 2, 3, etc. correspond to non-trivial primary field. That's that kind of conformal block. So therefore this A1 AI corresponds to Ni11, and we call this condenser of algebra because only depend on the Anyang label, we formally can write this as composite Anyang and the direct sum of several Anyang, but how many I appear depend on this A. And the AI is an integer, non-negative integer. So just a direct sum of several other Anyang. So this kind of composite, and this is very, very important. So in this way, we introduce this condensable algebra. Okay. So the claim is following. So I will explain those claims, but let me state the claim. And so actually, this is a boundary construct this way, coming from condensation for Anyang, from bulk Anyang to the boundary. Remember, when we consider Z2 gauge theory, we say there are several boundaries. One boundary E condensed, another boundary is M condensed, and there is nothing condensed. So this is a more general way to see which condensation give which. So this composite condenser algebra really describing condensing Anyang. So this A can be E, can be M, then get different boundary. But this is a formal way to do that. And then you can see which Anyang condensed from this expression of partition function in terms of conformal field theory. It's just a 1,1 component of this expansion. Okay, so that's one point. And the second point is that the condensation would break, spontaneous break conservation law, like in bulk, like a Z2 gauge theory. E have mode conservation. Then in the E condensed boundary, this mode conservation is spontaneously broken. And so therefore, therefore the categorical symmetry is broken down to something smaller. Okay, so there's a notion that we have a smaller categorical symmetry induced by anion condensation. So this is like unbroken symmetry. The unbroken symmetry have a corresponding categorical symmetry we call the M/A. So this kind of thing are also important. I will explain in a moment. Then whether the boundary is gapless or not depends on whether MA is trivial or not. The boundary can be gapped only when MA is trivial. If MA is non-trivial, the boundary must be gapless. So that's another way to say that in order to get a gap boundary, we should have enough condensation to completely break categorical symmetry. If you do not completely break categorical symmetry, the boundary must be gapless. So this is in recent years, there's a lot of discussion of a symmetry protect gaplessness. So this is the most general way to describe the symmetry protect gaplessness. We will have certain symmetry, anomalous symmetry is not broken. Then the state must be gapless. And but the most general way is a formula this way. What depends on whether unbroken categorical symmetry is trivial or non-trivial, determine whether it's a gapless or not. And just a moment. Then if we break, if A is large enough such that the induced topological order is trivial, then A is called the Lagrangian. Yeah, please.
Are you still talking about the discrete coefficient?
Yeah, the symmetry is always discrete. Yeah, we always talk about finite symmetry.
And I don't have any intuition. I mean, for association of a gapless space for the discrete symmetry.
Yes. Yeah, that is the amazing thing. The discrete symmetry enforces gaplessness. Yeah, that's a symmetry protect gaplessness include discrete. Yeah, this is a very good question because we know we are familiar that when we have continuous symmetry, we have a perturbative anomaly, like gravitational anomaly or even U1 anomaly, SU anomaly. It's well known that this perturbative anomaly of a continuous symmetry protect gaplessness. And here I try to say, even for discrete symmetry, and there's a similar phenomena, and this discrete symmetry protect gaplessness. Yeah, that's a kind of one of new result obtained from this kind of thinking.
So if you pick, for example, like just the Ising model as the conformal blocks you were building with, what would you find?
Yeah, I will give an example at this moment. Yeah. So let's get some intuition why we call this. Now let me explain why we call this coefficient condenser algebra. Why condensable? Why condensation? How that relate to condensation? So let's consider gap the boundary of a 2 plus topology order. So which is included here? Here I say conformal block look as a gapless, but the conformal block contain a gap situation where the conformal character is constant. If a conformal character is just 1, then there's nothing. It's topological, nothing. Then if a conformal character only 1 and alpha just 1 index, you replace 1 here, alpha only 1 index. So this whole sum just ni 1 1. That's your partition function. And and in this case, this partition function satisfies this condition. I can rename this Zi is ni11, also ai. So these 3 symbols just the same thing. Just in different place, I use different symbol for convenience. But as a partition function, it satisfies this condition, the modular convergent condition. Now the a just constant, non-negative integer constant. Okay, because a is just like one degeneracy, so that's so it has the constant. Okay. So in general, why you say this partition function is a ground degeneracy? Usually the partition function is a trace of a Hamiltonian. It's equal to this energy density times the space-time volume. That is partition function should be. But however, in the conformal field theory, we tune the energy density to 0. When you consider partition function in conformal field theory, there's assumption the energy density is tuned to 0, fine-tuned to 0. So I just follow the same tradition. Once you tune the energy density to 0, then the partition function is a ground degeneracy. Just this is the overall factor. So that's why this Z is a ground state general state. It should be this integer. That's one point. Then another point is that what A to 0 means. You know, A is labeled by this onion index. And some AI is non-zero describing ground state general state. And some AI equal to 0. So what's the meaning of 0? 0 means the following. You know, when you're inserting this, you know, what if you do that? Originally, we have a nothing here. We have a partition function. Then we insert a pair of onion and anti-onion, I and I bar in the middle. Then we move I bar to the boundary. If I bar can be absorbed by the boundary, then we have that situation that we have a I bar condense. And then that means AI non-equal to 0. If I bar cannot be absorbed boundary, so this onion do not condense, then that means creating the bulk onion means we must have a boundary onion as well. The boundary onion is not ground state. It's not part of the ground state. And when you have boundary onion, which have energy gap, when conformal field theory, energy gap means the partition function is exponentially small. Yeah. So that's 0. So therefore 0 means that this particular onion do not condense. Non-zero means it's condensed. So that's why we call the condensed algebra. So therefore interpretation is really that this AI non-zero means type I onion condensed on the boundary. That should be type I bar, but let's not worry about that. And 0 means the type onion does not condense. So therefore this condensed algebra describes pattern of onion condensation on the boundary. You know, which onion condense, which onion do not condense. Really describing that. And so, but the pattern of onion condensation on the boundary is really pattern for categorical symmetry breaking, just using Landau's picture. You know, condensation breaks symmetry spontaneously. So onion condensation also break categorical symmetry spontaneously. So that is the picture here. And then, so now I explain this induced topology order. Okay. So here, you know, here I try to say the onion condense on the boundary is something strange, you know. What do you mean by onion condense on the boundary? It's more usual to say the onion condense in the bulk. Like that's a Higgs mechanism. So in the bulk topology order, we have some onion. In gauge theory, we have some charge particle. The charge particle can condense like a Higgs mechanism. Change the topology order to something else, a new topology order. So condensation of onion in the bulk would change the topology order. But usually you can only condense the bosons. And you can only condense the boson with the trivial mutual statistics together. So that is just ordinary Higgs mechanism. So let's say that more formally we do the same thing. So this A just describe the onion which can condense together. Yeah. And after condensation, what do we get? What is the bulk topology order if onion in A condense? Well, first thing that is really the following. In the induced topology order, then those onions must have a trivial mutual statistics with A. Because A is like some order parameter. If you insert an onion with non-trivial mutual statistics with its order parameter, you create a branch cut in the order parameter, and then causing linear growth in energy. So that's confined. So A condensation confine all the onion with non-trivial mutual statistics with the onion in A. And also, if two original onion differ by some onion in A, then they are really equivalent because A condense. So whatever in A is all really trivial. If IJ differ by A, whether they are the same. So there's a reduction. So that's why this M/A/A quotient A, something like that coming from there. So this onion condensation is pretty complicated, but this is a rough idea how this onion the induced topology is obtained. And then we know, then the picture we have before is that in this cap space boundary is that if induced topology is trivial, so M/A is trivial, it's a product state. So usually if M/A is non-trivial, then then we'll have domain war between two topological order. This will be domain war. If M/A is trivial means the product state, we can remove them. Then it becomes boundary. Yeah. So therefore, if A is a Lagrangian, means M/A is a trivial. So that means if you condense enough onion to make M/A equal trivial, then this A actually describes a gapped boundary. Because outside trivial with product state can be removed. So that's the motivation that the condensable Lagrangian condensed algebra describe a gapped boundary. Then there are smaller condensed algebra. If some algebra is so smaller, it describes gapless boundary. So basically it's following. If condensation is large enough, destroy topology completely, we get a gapped boundary. But the gapped boundary is regarded as a gapped face in the original setup, original system with the symmetry. We have all kind of gap face. We can have symmetry breaking face. We can have a SPT face, SCT face, all that. Here the point is that all those gapped face can be obtained by the condensation to the boundary, but only condensation of this Lagrangian condensation, the maximum condensation. Then suddenly have something quite amazing. That is the Lagrangian condensed algebra classify gapped face together as a symmetry breaking, SPT, SCT in the same formalism. Remember, we developed this, this group, subgroup theory, symmetry breaking corresponds to symmetry breaking phase. And using group cohomology, we get SPT phase. But ICT is a very complicated, we have all kinds of complicated theory. But in this formulation, just a Lagrangian condensed algebra would classify all those phases together in a unified formalism. So that's one way to see that this categorical way to look, this categorical symmetry is a more convenient way to look at the symmetry. To have a more cleaner, more straightforward formalism to understand those phenomena. Then similarly, if this one is non-trivial, we should have a gapless boundary because of the following. And so you can see, so now we have original topology order in the bulk. Then you have some condensation, we get this new topology order. This pink one is a new reduced topology order. Then the reduced topology can only have its own boundary. Okay. And then you may say, well, this topology order MA may have additional onion condensation, but then we have too much. So what I try to describe here is that we want to use this construction to only describe a boundary with only A condensation. But A already condensed from M to M/A, A already condensed. So we should not have a more condensation here. If you have more condensation here, you have too much condensation. So therefore, we should have a so-called one condensation. Only the trivial part is condensed, but trivial part always condensed. So that means this MA have a one condensed boundary, which have no condensation, which is gapless. And this one condensed boundary for MA, and this composite structure can be viewed as A condensed boundary of M. So A condensed boundary of M through this domain wall can be viewed as a one condensed boundary of MA. Why this is convenient? Because this one is a gap. This domain was a gap domain wall. We are interested in the low energy physics, which can be viewed as a one condensed boundary of MA. So that's a reduction. For A condensed boundary of M can be studied via one condensed boundary of MA. We just need to calculate from M to MA, how M to M/A, this reduction. Then we can unify the theory of a gapless boundary. Yes.
So M/A is still a non-trivial topological order here, right?
Yeah, can be. If M
Yeah.
slash is trivial, then that means this M can have gapped boundary.
Okay.
If M slash is non-trivial, want to argue that, then if M slash is non-trivial, then we can say claim that the A condensed boundary is a one condensed boundary for MA, and the one condensed boundary for MA must be gapless if MA is non-trivial. So now we can study this kind of a question. And why? It's actually very simple. If MA is non-trivial, means it has some non-trivial ST matrix. Okay. What is the one condensed boundary of MA? M slash A. We don't know. But if you assume this one condensed boundary is gapped, then the gapped boundary is given by the constant. Their partition function is a constant integer. And since we insist it's a one condensed boundary of MA, this constant just is only one in the trivial sector. All other things do not condense, so it's 0. So this one should satisfy this modular covariant condition, which can never do. Because this S matrix, the first row is this quantum dimension, which is all positive integer, some positive, not integer, some positive numbers. When you have a positive number in the first row, then this kind of a vector can never satisfy this condition. Cannot be eigenstate of this SA with this A. So this is a very quick way to prove that the non-trivial topological order guarantee gaplessness. This is just a one-line proof. And so you can see that this whole thing. Yeah. Okay, I think I can skip that. There's some more condition A, and which is some more mathematics. So I won't go into this. I think the slide is upload here. You probably can get slide to see more. And so let me just not just in last 15 minutes, I just give some example. I think I can finish 15 minutes, just go through some example very quickly. So for the Z2 symmetry, the categorical symmetry is a Tor code, Z2 topological order in two-polar dimension. It have 4 types of onions in bulk. That means this T Z2 gauge theory and ST Z2 gauge theory is a 4x4 matrix. That's the ST matrix, just 4x4 matrix. Then to obtain gapped boundary, we just need to find a constant non-negative integer satisfy these 2 conditions. We find 2. So these 2 satisfy this condition. So that's a represent gapped boundary. And that's our old story. This is one is E condensed boundary, and that's M condensed boundary. Yeah. So you can see the first one is this identity always condensed. Second element is E, third element is M. So this is E condensed, this is M condensed. And there's also a smaller condensation. That is only one condense. E and M do not condense. If E and M do not condense, we have also solution. And so I can skip that. This is solution. The first solution is constructed using the 3-4 unit, actually the 4-3 minimum model is Ising minimum model. And why I say this is one condensed boundary? Because you can see this is primary field, Coulomb block for the trivial primary field, identity primary field. And so this psi chi0 square only appear in this component. In other component, so here we have chi0, but the other side is not there. So that means this solution is a one condensed because this character, this N11 only appear in the Z1. Yeah. So you can see that is one condensed. And similarly, using 5-4 binary model, we have this solution. Again, this is 0 Coulomb block, trivial Coulomb block only appear in the 1. So this is how we look at this. So amazing is that this one condensed boundary is not unique. There are several of them. So actually, indeed, knowing the bulk, we don't know boundary uniquely. And so the boundary bulk relation is the bulk do not determine boundary uniquely. So looks like Using categorical symmetry, we cannot determine the gapless theory uniquely. But however, I want to say the following. This one have a higher central charge. It's less stable. It's like fine-tuned. Then we usually refer to the most stable one with the middle central charge. It's the same thing as the following. So usually we say Z2 symmetry breaking is described by Ising model critical point. That one actually is an incorrect statement. If you just say Z2 symmetry breaking, the critical point can be many other things. The critical theory and the boundary you can stack with any CFT which don't couple to Z2 symmetry to the critical point, get a new CFT. So usually when we say Z2 symmetry breaking critical point is Ising model, we refer to this most stable minimal central charge CFT. And it's the same thing here. When we say categorical symmetry determine the gapless states, we refer to this canonical most stable states. So here we can see some example. And this is a tri-critical Ising model, I think. So there's some, you can reach there by some fine-tuning.
Simple question.
Yeah.
So in the previous slide, so in En and condensed phase, what is the Lagrangian subalgebra? Will you repeat based on that example? Yeah.
Maybe here. You can see here in this picture that the condensed algebra is a 1 plus m. This is one of a Lagrangian condensed algebra. Their condensation break this dual symmetry but have an original symmetry. So this is this m condensed boundary is a Z2 symmetric phase.
Yeah. What is the condition for the Lagrangian subalgebra? Sorry, you explained.
Yeah.
Okay.
Let me just say that very simply is a simple statement. Maybe it's easier to say here. Yeah. So this A describe condensed algebra. So you can see this is a condition on the condensed algebra. Yeah. And actually this the A side of this condition is a Lagrangian. Yeah. And so actually, and it goes through the following. So actually, A can be more general, can be smaller. So actually, condition for condensed algebra is this set condition, which I don't have time to derive. Actually, I do not plan to derive this condition. There's some mathematics. And so like A should be integer, non-negative integer, and the A is non-zero only for bosons, you know. This one is not even non-trivial. So use this A should have this kind of condition. This is equal to cyclotomic integer, some number theory thing. And if A is Lagrangian, they have this additional two condition. So in previous condition, if A satisfies previous condition, you may get a Lagrangian or non-Lagrangian condensed algebra. But the Lagrangian one satisfies this additional condition. That's the maximum. In some sense, you can say that the Lagrangian one is roughly speaking the maximum condensed algebra. Non-maximum one is a non-Lagrangian. So the basic thing that. So this is really fancy way to discuss Higgs field. All we talk about the Higgs condensation. What kind of particle can condense together? But those particles can be anyons, can have quantity dimensions. When that happens, this became quite a sophisticated theory. The Higgs condensation is became sophisticated. So this really the theory for Higgs condensation, but allowing Higgs field to have a non-trivial quantum dimension, some kind of boson, but also non-abelian anion at the same time. Yeah, and so really just describe what kind of thing can condense together. And in this example, we can have this Z2A, Z2B, we have two Z2 symmetry, like two toric code together. So we have a EA, MA, EB, MB, just generated this charge and a magnetic flux in a toric code. And then we can have all condensed module. For example, we can condense all the flux. We have condensed MA, MB, and their combination. Then charge is not condensed. Then this one describes symmetric states. The both Z2A symmetry and Z2B symmetry. The Z2 symmetry is not broken. And here we can condense the EB, but do not condense the EA. So that means the second Z2B is broken, but the Z2A is not broken. So you can see that by designing Higgs condensation, we say which symmetry broken, not broken. So it's pretty normal. You know, what's new? That's a Higgs condensation, symmetry breaking. The funny thing is the last example. We can, and those combination are bosons. You can check the bound state of EAMB, EBMA, and this, they are all boson, and they have trivial mutual statistics. Using Tor code, you can check indeed, and they can condense together. And when they condense together, you break symmetry, you destroy the topology order completely. You get trivial topology order. So they are Lagrangian. And this one, it's hard to say you break any symmetry. You want to say EA condense, but they condense only combine with the MB, so they don't condense by themselves. So therefore, Z2A is not broken, and the Z2B is not broken. But there is some condensation. So actually, this is Z2A cross SPD state. So this is an example to show that the maximum Lagrangian condensed algebra actually can capture SPD state. Yeah. This may be the simplest way to understand SPD state without using group cohomology, just using condensation Higgs. You get SPD state. So I think this is pretty cool. Yeah.
Excuse me.
Yeah.
Is it, I mean, generically true? I mean, this statement, I mean.
Yeah, we claim generally true. And actually, the mathematician prove is generally true. So actually, from this, you can get a group cocycle.
Right.
Yeah, for general group G, you say different symmetry non-broken is labeled as cocycle. You can recover group cohomology. So this is pretty non-trivial. Yeah, because it's a totally different way of thinking, but you get same result. Yeah. But here, just give you an example to say, yeah, this kind of thing can be true, but actually, for general group G, I just do the Z2 cross Z2. For general group G, this is also true, and labeled by cocycle. Huh? Yeah, can be non-abelian. The G can be non-abelian. This is also true. Yeah. For higher group, I don't think there's a proof because in this case, just a two-dimensional topology with modular tensor category, we know a lot of results. For higher dimension, you need a higher category, which with less results. Okay, so let's skip this part. So last 5 minutes, let's go through these three. S3. So S3 is symmetry. The Categorical Symmetry is S3 gauge theory. Yeah, we have 8 types of onions. There's a fusion rules. We described this a little bit. Okay. Then we can study their condensable algebra. So there's 8 of them. There's 8 condensed algebra. Okay. The first 4 is the Lagrangian. So they are maximum, cannot be extended. The second 4 is a non-maximum. So they can be enlarged. Like this one can be enlarged to this, become bigger. And this one can be enlarged here. The maximum number. So therefore, expect this first 4 to describe a gapped phase, which should include the symmetry breaking state, SPD state, ICD state, etc. And here, it happens to correspond 4 symmetry breaking states. Like this, BC is a flux. Remember here, I should explain. The BC is a S3 gauge flux, and the A1, A2 is a S3 gauge charge. The A1, A2 is a representation of S3, and the B and C is a corresponding flux. And the A1, B2, the B1, B2 is a bound state between these 2 representation with the B, and the C1 is a bound state of 2 representation with the it's C. So it's a bound state. So here you can see that both A1, A2 condense. It means both charge condense. If break symmetry completely, you get a Z1 phase. Here charge not condense, only flux condense, so we get an S3 phase. So you can see that, and we only have a 4 phase. no SPT states. And you check the S3 group have no non-trivial H-2. So they agree, for S3 symmetry, there is no SPT phase. The only signature breaking phase. Yeah, we did get that result. And this diagram maybe is a thing. You can see this four corner is this condensable maximum condensed algebra or Lagrangian condensed algebra. They call some gap phase. I draw this in particularly this smaller condensed algebra is included into this and included into that. So it looks like when you go from one gap phase to another gap phase, the critical theory described by this smaller condensed algebra, which is gapless. Or maybe you can go around like this. It's even smaller. You can go through this, you know. So from here you can imagine maybe there's a pattern of group inclusion, non-inclusion of algebra describe the relation of phase transition. This part is shaky, you know, it's maybe more complicated, but I just have some idea. This may be another way to rebuild the global phase diagram using this relation between condensed algebra. So that's really come to yeah. So actually we can we can solve for one condensed boundary. We get this a 6-5 minute model and things. We can go through this. So for this non-Lagrangian condensed algebra, we can get the CFT. But the main point I want to say is following is so this is one of the phase diagram we have. So I put in the same similar topology as this graph figure here. Second thing, this let's see some familiar. Select a Z2 to Z1. That's ordinary Z2 signature breaking transition. So this transition is described by this condensed algebra. This A1 plus A2. It turns out that when you have S3 gauge theory, when you condense A1 and A2, you break S3 gauge theory into Z2 gauge theory. Actually, this A2 is one Higgs field in two-dimensional mutation. When you condense Higgs field in two-dimensional mutation, you get Z2 gauge theory. And the one condensed boundary of Z2 gauge theory is a 1 plus A2 condensed boundary of S3 gauge theory. And one condensed boundary of Z2 gauge theory is an Ising critical point. So this line indeed Ising critical point as expected. Yeah. Then so other critical point you can understand the similar way. You know, you can so like a 1 plus A1 Higgs condensation break S3 gauge theory to Z3 gauge theory. So this line became this parafermion CFT. The trouble is this one. So the S3 to Z1 transition, that S3 is here, Z1 is here. What is their critical point? Well, they're connected by one there. You can see usually this picture. This S3 and Z1 is connected by this minimal condensation, just one condensation, nothing condensed. And so therefore we think this from S3 to Z1 should be this one condensed boundary CFT. From S3 to Z2, you can look at this. And these two algebra share 1 plus C. You know, 1 plus C is shared by these two algebra. So therefore, their phase transition should be this 1 plus C condensation. But amazingly, for S3 symmetry, 1 plus C is not condensed algebra. They do not satisfy that condition. It's missing. This 1 plus C is missing as a valid condensed algebra. So this puzzle, you know, what describes S3 to Z2 transition? It turns out that it's a one condensed boundary. Actually this S3 to Z2 critical point is described by one condensed boundary. So using previous slide is that S3 to Z2 is go through here. There's nothing here. So then we have trouble. Then S3 to Z1, what describes S3 to Z1? You know, this one already described this one. maybe this same critical point also describe S3 to Z1. We're in a very strange situation. Two different symmetry breaking patterns describe the same CFT. That's very strange.
So S3 to Z3, 1 plus B is condensable? For
Yeah.
S3 to Z3.
All these are condensive algebra.
Thanks.
Yeah. The one in this picture, all condensive algebra. The missing one here is illegal. So that's a wonderful non-trivial result they get. Yes.
Elementary question. So from one condensation, suppose I describe some Ising, so A2 condensation.
Yeah.
So then how can I make such A2 condensation in this partition function?
Yeah, it's this. So actually, I skip here. Yeah, this is A2 condensation.
Yeah.
So solving, actually, I just using this 4-3 minimum model and solving this equation. This is a solution. You can see that the chi0 appear here. That's a 1. Also appear here. So that means 1 and A2 condense. This black one means which one condense.
I see.
Once you get the CFT solution, you can figure out which one condense. They correspond to which condensation. Yeah, really by looking at these two, that's 1 and A2 condense. And 1 A1 condense, there's this 1 condense and A1 condense. And other things do not condense.
So just pull those.
Yeah, once you get this solution,
okay,
this solution carry a lot of information. You can read out from it. That's a very good question. I didn't have time to explain this part. Yeah. So solving this solving using conformal character, constructing partition function, you can read all the information from the solution. Yeah. Okay. So this is the first non-trivial result. This S3 to Z1 critical point, we have a trouble. They are either the same critical point as a S3 to Z2 transition, as a post-model critical point. I don't want to believe that. That'll be really strange. Or it's another critical point with central charge, very large central charge, and beyond the 1. There we did not explore. Below 1 is the minimum model we explore is not there. And beyond the 1, maybe there's something there. Or maybe the stable transition just do not exist. So that's also a possibility. And so this Landau a lot of transition do not exist as a continuous transition. That's also possible. At the moment, I'm thinking inclined for the second possibility. Maybe this one is more likely. Yeah. There's another thing. So there's a four-phase critical point. There's also still a 1 condenser boundary. So still describe this 1 condenser boundary. But which one? So there's an issue there. Let me not say, finish up just 1 minute. Just want to say one more thing. That is, there's a duality. This A2 and B is very similar. If you look at the fusion rule, at first they have the same quantity dimension and the same spin. If you look at fusion rule, this NIJK, this is a fusion rule table. This fusion rule table is invariant under A2B exchange. So this is like an EM exchange. This is like a duality. But S3 have a duality similar to EM exchange in the Ising model or a Torah-code model. So this duality is like a horizontal reflection of this graph. Just this straight line just do the mirror reflection of this straight line. So S3 map to Z2, Z3 map to Z1. And that means that S3 to Z3, okay, so it really means it means that this S3 to Z1 transition is mapped to Z3 to Z2 transition. That is surprising. Yeah, basically it's this. S3 to Z1 is mapped to Z2 to Z3. So that means these two transitions have same property. If S3 to Z1 is a continuous for some system, then for some other system, Z2 to Z3 should be continuous. Duality is not self, it's mapping from one system to another system. So in some system with S3 symmetry, if you see the S3 to Z1 continuous transition, then there's corresponding mapped system with S3 symmetry. From that system, you should see Z2 to Z3 continuous transition with the same critical point, same exponent, same scaling exponent. Then we usually say that Z3 to Z2 continuous transition not allowed, it's lambda forbidden. Then that means that S3 to Z2 is not allowed. S3 to Z1 is not allowed. So this is maybe this is one of last application I want to discuss. So there's a duality transformation, and so we see this transition in the different lights. Yeah. Thank you. Sorry, I really ran over. Yeah.
Now the talk is open for questions.
Yeah.
About this last statement about this duality, which
Yes.
is the transitions in different systems. I mean, they still have to possess the S3 symmetry originally, right?
Yeah. So the point is that because this is automorphism of categorical symmetry, that means that before mapping, after mapping, we both have system of S3 symmetry. Yeah. So, but however, and there's a this is different from the original dual symmetry. There there's a mapping is different. Yeah. This is automorphism. That one is like reliable. Yeah, I don't know what to say. Yeah. Yeah, automorphism have this kind of feature. So actually this is not unique. What I try to say, there's a lot of categories, a lot of topological order have this automorphism. Automorphism is not uncommon in the diagraph written theory and all this theory. And whenever you see automorphism, you have this very funny mapping of symmetry breaking transition. And so this is just a very simple example of that. And there's if you look at the automorphism of topological CFT, MTC, module tensor category, you identify a lot of this strange relation, surprising relation. Yeah. Yes.
For the Z2 symmetry breaking, you mentioned the principle that you take the CFT with the lowest central charge,
yes,
because that's the most stable.
Yeah.
But for if the S3 to Z2 symmetry breaking is if that transition were described by something with central charge greater than 1,
yeah,
that would seem to, in this case, violate that principle? Or
yeah, thank you for the question. And
if the second option were correct.
Yeah, it's a second version. The point is that I kind of cheat a little bit about the stability. I say lowest central charge is most stable, which is correct. But when you say stability, we should count the relevant operator, not counting central charge. So I can say the CFT with the minimum number of relevant operators is more stable. Actually, this is more precise. So there's two ways to define stability. And using central charge is a little bit theoretical, not relevant. In this discussion, I should use relevant operator to do that.
Okay.
And this transition is a general transition. So we're looking for the CFT with one relevant operator, one symmetric relevant operator. And indeed, this CFT, what is a 6-5 minimum model CFT, indeed have only one relevant operator describing this S3 to Z2 transition. And actually there is another CFT, which is central charge is 5/6. And that one also describes this one condensed boundary. It's another solution of the same equation. But that one have two relevant operators. So that one, although exists, but cannot describe this transition, because this transition is only one relevant operator. So we are in a very interesting situation. When you increase the central charge, CFT become more unstable. They have more relevant operator. And we already find the one with central charge 5/6 with the two relevant operator. And the second condition means that we have some even more unstable CFT, but with less relevant, only one relevant operator. That one should exist. So that's a little bit surprised. We already have a smaller central charge CFT with two relevant operators. Then we expect to finding some CFT with a more central charge, but more stable. It's kind of counterintuitive. But actually, we are frustrated here. You know, all this solution looks surprising and strange. And so we have to pick a least worst one. Yeah.
More questions?
So can you give me some just one or two examples which are gapped, but I guess which is nevertheless non-trivial.
Yeah, I don't know. It's so the first four is this four condensed algebra is a corresponding gap phase. They're a little trivial because they're all symmetry breaking. And the non-trivial example is this one. They are gapped, but do not break any symmetry corresponding SPT state. Yeah. So the example here is like if EA condensed, that means Z2A would have broken. If EB condensed, Z2B would have broken. If both EA, EB condensed, they both broken. So this is totally too simple how they break. But here we have a very interesting condensation, which do not break anything, but also is different from the first one. First one is the Z2 symmetric, but only M condensed. Here is combination of E and M condensed. You get this SPT state. Yeah, you can see that maybe this may be the gapped case, gapped example, which is interesting. Yeah, this is non-trivial. It's just another way to look at the SPT states. Yeah.
So in the previous G2 gauge theory case, so if you consider only one condensation, you have two critical series.
Yes.
So in the G2 gauge theory, we have only two options: E condensation, either E condensation and N condensation.
Exactly.
So when such critical theory appear? So if I map in this S3 gauge theory.
Yeah, thank you. It's here. You can see we have a this E condensed here. That is, we have a symmetry breaking state. M condensed, we have symmetric state. Then we have a situation where only one condensed. Actually, one is another condensed algebra. This is legal. This one is legal. And this one condensed boundary. This one is not Lagrangian. So this boundary is a gapless. And this gapless state happen to be the critical point between these two gap phases. And also it's nice because this one can be included in the first one, also one can include the second one. So you can imagine you go from here to here, this one's M condensed, then M become uncondensed, reaching one, then after that E condensed, you get here.
You have two critical theories.
No, the point is following. This E and M have non-trivial mutual statistics. Actually, this is very important. They have non-trivial mutual statistics. When M became less condensing, E want to be more condensing because they kind of like this. If one condense, exclude the other condense. So when you try to make M less condensing, E want to become more condensing because they have this non-trivial coupling. And so therefore the transition happen together. M become uncondensed, E will condense immediately. So only at the one point, we have this condensed algebra. So this is a critical point.
Yeah, I'm so confused.
So there's no transition. So this is not the phase. This is not the phase.
Point, you have two critical theories.
No.
Tri-critical and
tri-critical. That's another. This is one condensed boundary.
Yeah,
this one condensed boundary have your solution not unique.
Yeah, two. You have two.
So you have two. This is I think this tri-critical.
Yeah. How can?
So in general, we have I think because there's only one relevant operator. When you further tone a parameter along this critical line, you may reach tri-critical one because this one is more unstable. Both are allowed. Both are one condensed boundary, but this is generic one condensed boundary. This is fine-tuned one condensed boundary.
But in the same bulk,
Same
you
bulk,
have
same
the
symmetry. Yes.
two.
Yes. So that's the point that the categorical symmetry do not determine the boundary uniquely. And but if you say they may determine the stable boundary in some sense more or less uniquely. Yeah. So yeah, this is the subtlety. Yeah, this is the subtlety in applying categorical symmetry.
More questions? Okay, if not, yeah, thanks. I will say, okay, before finishing this, lecture series, I have to mention, so without the support of our administration staff members, particularly Miss Mirin Lee and Kyung-tak Ryu, not here, but yeah, without their helps, it's very difficult to, smoothly use, this kind of lecture series. So let me give them big applause. Yeah, thank you very much. Let's end the Professor Wen's lecture series. If you are interested in tomorrow in Department of Physics, IBS, so you already get some announcement too. Yeah. From 4 p.m. there will be some seminar of Professor Wen in Department of Mathematics. So IBS. So concrete place, I don't know. Already announced to
Yeah,
So-
I like to also thank the audience. You asked so many good questions. Yeah, make it very lively. I really enjoy it. And usually it's the audience is more tiring. For the speaker, we thought about this kind of thing, so it's easier. But went through this 8-hour torture is not easy.
at least 10. Yeah. Thank you very much. Yeah.